Very good. What I would like to do in this second half of the lecture is, having discussed how the interpretation of entropy as a measure of amount of missing information can be criticized, let us look at the issue now of why does it work so well? What can we do with it? And the idea is then to use this method of maximum entropy to introduce the method of maximum entropy as a method to assign probabilities. The idea is actually rather simple. The bottom line here is that when we want to assign a probability distribution, we would like the probability distribution to reflect those things we know, but also to be maximally honest about giving large uncertainty to all those things we do not know. And of course, the large uncertainty means large entropy. So how do we proceed to do this in detail? Let me write those things down. And I'm going to see the method is going to assign probabilities. So we want a probability distribution that agrees with what we know and is, I would like to say, maximally honest and about the things that we do not know, and reflects large uncertainties about what we do not know. So if we were to write this mathematically, what we would like to say is we want to choose among all probability distributions. You can, for any probability distribution, you can compute the entropy. So what we want is a distribution that reflects the fact that we have very little knowledge about almost everything. So we want to choose that probability distribution, choose the distribution that maximizes entropy, but agrees with everything that we know, that agrees with what we do in fact know. So it maximizes entropy in order to guarantee that we're maximally ignorant about everything out there, but agrees, maximizes entropy subject to constraints on the information or the knowledge that we actually have. So, quick example of where this is going. We're going to explore this example to death in the next few lectures. Suppose you have a gas of molecules, and we know the expected value of the energy. So what we would like to know is a probability distribution that gives me the right expected value of the energy, but it is maximally ignorant about absolutely everything else. What this means, for example, if you ask what is the position of particle number 237, well, I have no idea. That's a correct answer. So our probability distribution should actually tell you that the particle has equal probability to be anywhere inside the volume that contains the gas. So it's, on the other hand, it's maximum entropy. On the other hand, it agrees with what we know. It's sort of interesting that when you think about it, the principle of maximum entropy ends up being like an ethical principle. It's a principle that tells you that you should be maximally honest about the things you do not know, while also being maximally honest not to ignore those things that you do know. Think about that, that the whole way we end up conducting science ends up being driven by a philosophy that is firmly consistent with ethics, with laws of or rules for behavior. That's something that it's an interesting part of philosophy that should be explored a little bit more. How do you make philosophy, ethics, quantitative? Very good. So let me give you an example of how we actually do this. We want to maximize an entropy. Maximize an entropy subject to a constraint. So I'll start with a simple example to describe the mathematical techniques we use, because although I'm sure you've seen this before, typically we see these things, namely the method of Lagrange multipliers. We see these things very early on in our student careers, and when you're pretty mature, and so you see it, you use it, proceed. But it's also very important to see it later when you're more mature, because then you understand exactly what the principles involved are all about. So here, suppose you have a discrete variable that goes from 1 to n, and here is the entropy. And in this particular case, I want to address the fact that we know absolutely nothing about this object. This is a die with n faces, and we know absolutely nothing about it. What probabilities do we assign? So the only thing we really know about the probabilities we only know that these probabilities add up to 1. So we only know the normalization, that the probabilities ought to be normalized. Apart from that, we do not know anything. So how do we solve this problem? Well, we want to maximize S. So first, I'm going to do it wrong. The purpose of doing it wrong is to see where the error arises, how it is that we have a problem, and then we're going to fix it. So to do it wrong, we're going to say, well, we're going to maximize this entropy. So we're going to vary the probabilities. A small variation in the probabilities leads to, well, here we have delta pi, vary the pi, log pi, plus vary the log. So that when you vary the log, you have the original pi, the variation of the log is 1 over p, delta p. And of course, what we're going to do is we're going to set all of this equal to 0. Let me first collect all these terms. Log pi plus 1 delta pi, and we want to find a maximum, so we're going to set all of this equal to 0. So now, so far nothing is wrong here. This is completely correct. A small change in the probabilities will cause a small change in the entropy. If you want the maximum, you set that small change equal to 0. Nothing wrong here. Now we're going to say, well, if the PIs are independent, if the changes are independent, then in order for this quantity to be zero, it must be the case that each coefficient, the coefficient of each delta pi is equal to 0. Then log pi plus 1 equal to 0. Very good. Why is that? Well, if this, what does it mean to say that these guys here, the delta pi's, are independent? By independent here, what we mean is that you can change one of them independently of all the others. In particular, you can keep all the delta pi's equal to 0, except for delta p1. So all the delta p2, 3, 4, 5, all those are zeros. Only delta p1 is non-zero. And so in that case, the sum disappears, and you only end up with the term with the I equals 1. If that is supposed to be equal to 0, then that tells you that log p1 plus 1 is equal to 0. Now you do the same thing with delta p2. All the delta pi is equal to 0 except I equals 2. That tells you that this coefficient with pi equals 2 is equal to 0. And so on. If all the pi's are independent, then this is equal to 0, which implies that pi, let me see, get the plus 1 onto the other side, you have a minus 1, then take the exponential, and you get the exponential of minus 1, and this is your answer. The pi's that maximize this expression are going to be 1 over e. And now you see you have a problem. The problem is that if you add, to check the normalization, add all the pi's, then what you get is the sum of all of these n terms of 1 over e, and this is just n divided by e, which is not equal to 1. So if we assume that these delta pi's are independent, your probabilities are not normalized. What we want is we want to maximize the entropy, imposing the constraint that the probabilities be normalized. So we want to impose. So this is wrong. Having figured out what the problem was, that you're not normalized. So what we want is the sum of the p's to be equal to 1. So what we want is the sum of the p's to be equal to 1, which implies that if you're going to do a variation of this, the variation of this equation, this should add up to 0. So what this means is that you're not allowed to vary them independently, vary the delta pi's independently. If you vary one, if one of the delta pi's is positive, then some other delta pi's are going to have to be negative in order to compensate so that you get a 0. You're not allowed to vary them independently. The variations have to satisfy this equation here. So how do we incorporate that constraint into the variation problem? The way we do it is we say we want delta S to be 0. Yes, it has to be a maximum. So what I'm going to do is I'm going to add 0. We want a maximum of S. That's the delta S is going to be 0. We want these guys here also to be satisfied. So clearly this is going to be 0. And we're going to do this with any parameter there. This is the method of Lagrange multipliers. This is where we introduce a Lagrange multiplier alpha. And this is the variation that we're going to set equal to 0. If you think about it, it's exactly the same thing we wrote here, right? It's exactly the same thing, except that I have added 0. So now let's do the variation with that added 0. And the way this would work is we're going to have the variation of S. So here we go. It's going to include the minus the sum I equals 1 to n. Then there is, let me just cheat and go back because we've already done it. Here we have the variation of S is going to be minus the sum log pi plus 1 delta pi. Log pi plus 1 delta pi. All of this is going to be equal to 0. So that's the variation of the S. Then we have minus alpha, so there is minus alpha plus alpha, and then we have the sum of the delta pi's, the sum of the delta pi's. So that's all there is to it. So let me just clean this up. Very good. So now, what do we do here? Well, we know that these delta pi's are not independent, right? So just like here, these delta pi's are not independent. When we look at this equation here, they're still not independent. They're still not independent. But now we have access to this alpha here. We know that the delta pi's are not independent, and so, for example, when you look at this equation here, we know that all the delta pi's have to add up to 0. So let us choose one as being the dependent one. We can say that delta pn is minus the sum of the delta pi's for I equals 1 to n minus 1. So you can pick these delta pi's for I between 1 and n minus 1. You can pick those independently, but then delta pn is fixed. So what do? We choose alpha. Remember, alpha was completely arbitrary. Choose alpha so that the log of Pn plus 1 plus alpha is equal to 0. So if we choose that alpha so that this coefficient vanishes, then the delta pi's for I equals 1 all the way to n minus 1 are independent. And this implies that for the remaining ones, remember there is the term with I equals n has dropped out. We only go now to n minus 1. For the remaining ones, we have log pi plus 1 plus alpha equal to 0. Very good. It's interesting that this equation looks very much like that equation. Therefore, log pi plus 1 plus alpha equals 0 for all i's, all the way to n now. So this is the bottom line. When we do these calculations in the future, we're not going to repeat this as just selecting one that is dependent on all the others. and then just focus on the independent ones. We just go straight. Once you have it here, you say, then these guys are all going to be 0. Some of these guys are going to vanish because the alphas, the Lagrange multipliers, are chosen to vanish, and the others are because this guy is independent, so all of them are going to be 0. So then this means we can solve this equation now, and we have log pi is equal to -1 minus alpha, and therefore pi is the exponential of -1 minus alpha. And now we're in good shape. It's interesting that this is a uniform distribution. This happens to be constant. Look, there is I on the left-hand side, but there is no I on the right-hand side. The distribution is uniform. If you didn't know anything about the die and you just figure out the distribution of maximum entropy, it turns out to be uniform. Now, how about the Lagrange multiplier to find the, let me see, the multiplier alpha is determined by requiring that the constraint, namely the fact that you want normalization, be satisfied. By requiring that the probability is here be satisfied, what this means is that I equals 1 to n of this constant must be equal to 1. So what we have here is n terms multiplied by the constant equals to 1, which means that whatever this constant here is equal to n. And therefore the probabilities, which are given by, well, here are the probabilities, right? This is 1 over n. As expected. So what we're going to do a lot is use this exact same technique to figure out probabilities that apply not only when you do not know anything except normalization, but when you know something else. At this point, we didn't know anything, we got the uniform. In fact, caution. Sometimes people think if you do not know anything in a problem, you should assign a uniform distribution, namely 1 over n, because of Laplace's principle of insufficient reason. Laplace's principle of insufficient reason. What this principle says is that if you have no reason to prefer one phase of the die over another, then you should assign equal probabilities to all the phases. Pretty cool. What's being reflected here is not necessarily the symmetry of the die, but the symmetry of your state of ignorance about the die. You have no idea what's going on with the die, same probability. Of course, if the die happens to be biased, and you do not know which way it's biased, this is still correct. But if you start tossing the die a few times, you may actually be able to do some inference, use Bayes, in order to figure out which way you should bias the probabilities. But the point I want to make here clear is that it's fairly obvious that we have sort of derived, Laplace's principle of insufficient reason from MaxEnt? In a sense, yes, we have done it. We just did it, right? We maximize entropy subject to only the constraint of normalization, and you get the uniform distribution. So in a sense, yes. But you have to be very careful because in a sense, we have not. Because the formula for the entropy that we use to maximize maximum entropy was derived from Shannon's axioms, which included as one of the axioms, axiom 2, in fact, the fact that the uniform distribution was special, right? The uniform distribution is considered a very special case in the Shannon approach. And so in a sense, what we have said is we have derived the formula for entropy in such a way that is going to be consistent with Laplace's principle of insufficient reason. So my answer is, have we derived the principle of insufficient reason from MaxEnt? Well, not quite. We derived entropy to be consistent with the principle of insufficient reason. Actually, it went the other way around. Very good. Let's do another example now. Let's get more, so that it gets a little bit more interesting. So what we want to discuss, we want to discuss the so-called canonical distributions. Little digression. The term canonical is used everywhere. For example, when you talk about, in mechanics, you talk about coordinates and the corresponding momenta. You call them the conjugate momentum. You call it the canonically conjugate momentum, right? Here we're talking about canonical distributions. Clearly, this canonical here, the canonical distributions, and the canonically conjugate momentum have nothing to do with each other, right? And yet, what does canonical mean? Canonical just means according to the canon, according to the practice. That's all, according to the rules. You follow the rules, this is what you get. So we're going to follow rules for determining some distributions, and because we're going to always follow the same rules, we're going to call them probabilities according to the rules, canonical. Of course, it has connotations of church dogma. You follow the canon, you follow the rules, and that's exactly what we're doing here. Very good. So what is the distribution we want to derive? We're going to, we have a discrete variable, I equals 1 to n, and we want a distribution such that not only it is normalized, so I equals 1 to n, but also we want it to be to satisfy a constraint. And we're going to do this as follows. We're going to say the constraint is going to be an expected value of some function. So this is going to be some expected value, some number. Let's see. We can have one constraint and we can have many. So let me put a k here. This is an index, an upper index, and we can have many constraints. So this is going to be 1, 2, and so on. You can have as many constraints as you want. The one limitation in this special case we're considering here, maximize an entropy subject to normalization and constraints on expected values. The limitation is just that we are doing constraints that happen to be linear in the probabilities. The method of maximum entropy is not limited in this way. Any kind of constraint um, is fair game. You can, if that's information you have, that's information you have. You can do it. What happens is that these constraints that happen to be linear in the probabilities are the ones that we can implement nicely using the method of Lagrange multipliers. So our restriction to linear constraints here is only because we have a method that allows us to solve the problem. So we want to maximize the entropy, and we're gonna just write it out. And we're gonna set delta S equal to 0. And we're going to, just like before, we're going to add a Lagrange multiplier for the normalization. So we added 0 here. And now I'm going to also add another Lagrange multiplier for the constraint on the expected value of f. And here you can see that I've added another 0. And I set all of this equal to 0. Now, if you have many constraints, you're going to have many terms that are added here. And I'm going to put k there. You need one Lagrange multiplier for each constraint. And very good. So this is it. And there is going to be a sum over the case. So notation. When you have something, a sum in which you have a lower index and an upper index, this we're going to write it as just lambda k fk. So whenever you see an index down and another up, and you just see them like that, you're supposed to imagine that there is a summation, but then we don't have to worry about writing that symbol, right? It makes the notation a little bit easier. Now at this point, I can see somebody here in the audience saying, oh, I've seen this somewhere. When you do special relativity or general relativity, whenever you have repeated indices, you're supposed to add. Yes, this is called the Einstein Convention. And so you're going to do things in special relativity. You may end up doing things like P mu is minus mc squared, right? Things like that, right? You do that all the time, lower and upper indices. Very good. You may also remember that vectors come with upper indices, while gradients and covectors come with lower indices. Could it possibly be that the professor here is writing lower and upper indices in anticipation that at some point in the future we're going to have interesting geometrical properties? Precisely. So the notation is useful not only because it allows us to not write those summations, but because keeping track of upper and lower indices is going to have interesting geometrical significance later. Very good. So now let's do our variation. When we do the variation of S, we're going to have minus. There is going to be the summation over all i's of log pi plus 1 delta pi equal to 0. So let's remind ourselves what we were doing. It's exactly this thing. The variation of delta log s is the minus, where I look back, too many deltas, right? The variation of delta s is this guy multiplied by delta pi. That delta there is wrong. There is no delta there. Very good. So let's keep going. Here we go. Here we have the variation of delta s minus alpha. There is a minus, and that's where the minus is, plus alpha. The variation of the pi is the sum of the delta pi's, so that's taken care of. The variation of 1 is 0. And then here we have another minus, so this is going to be plus lambda k, and then there is going to be the sum, which is out here, of the delta p's, which is there, multiplied by the f. And then there is the variation of this number. So now we're going to assume that, of course, these guys are not all independent, but we have all of these Lagrange multipliers that we can play with. So we choose the alpha so that delta Pn has a vanishing coefficient. We choose lambda 1 so that delta Pn minus 1 has vanishing coefficient, and so on. And so the net result is that we can just set log pi plus 1 plus alpha plus lambda k f k equal to 0. So this, yes, that is all equal to 0. And so therefore now we can just isolate the pi. Is going to be the exponential of minus 1 minus alpha minus lambda k f k. So there you have it. That's the probability distribution when you have not only a constraint on normalization, but also a constraint on the expected value of this f. Maybe I should have written this a little bit more clearly here. This f is a function of whatever variables you have, the I. So the f's that we should be writing here, sorry about that, there is an I here, so there should be an I here. My mistake, apologies. I. Right, that's the pi goes with an fxi. Let's just write it like this. And then here we have an I. So now the probabilities, if it were just this factor, the probabilities would be independent of I. But because we have a function of whatever variable you have over there that depends on I, then you keep it. Alpha and lambda are determined from the constraints. To find alpha, impose that the normalization add up to 1. So we impose the fact that the PIs add up to 1. And what this means is that minus 1 minus alpha, the sum minus lambda k f I k from 1 to n equal to 1, which tells you that 1 plus alpha, get this factor here onto the other side, is equal to like that. So from here, we find what the alpha is. Now, this expression here is typically written as, because this is going to be like the normalization up here, this we're going to just write it as z, and we call it the partition function. And this is a function of all the lambdas, of lambda 1, lambda n. It is not, please notice, it is not a function of the i's. It's not a function of I, because the i's are being summed over, right? The only, and these functions are whatever they are, they're just fixed. So different capital F's, different Lagrange, different expected values will lead to different lambdas, and this is what we have there. Sometimes also, it's common to write the 1 minus alpha that we have over there. Yes, it's right, the 1 plus alpha, you write it as lambda 0, as if it is one more constraint, one more Lagrange multiplier. That works very nicely also. So pi can be written as e to the minus lambda 0 minus lambda k f ki, and remember there is a summation over these guys here, or pi is 1 over z minus lambda k f ki. These are the canonical distributions. We have figured out what the Lagrange multiplier alpha is supposed to be. It's supposed to be this sum. But what are the lambdas? To find lambda k, we do the same thing. We just impose that the expected value of pi fi k be capital F. And so we just have to write it out. So let us do that. I'm going to write it explicitly. There is going to be the exponential of minus lambda k f k I, all divided, multiplied by f I k, all divided by 1 over z, and this is supposed to be equal to f k. So the trick that we use here is that if this fk were not there, then this would just be the partition function and it would cancel. So the trick that we use to write this in a conveniently clever way is to say, if I were to have just the partition function and I take a derivative with respect to lambda, I get the fk in front. I get this. So the expression that we want is something like this. If I take the derivative of the partition function and let me use another letter here, L, because here I'm summing, and here I'm just taking the derivative with respect to that. This guy is supposed to be 1 over z e minus lambda k f k I f l k. So, right? Taking the derivative with respect to lambda brings minus f. Okay, so I forgot the minus. Here's the minus take the derivative with respect to lambda L brings FL in front. That's what it is with a minus sign. And this is supposed to be FL. So that what we have is the derivative with respect to lambda L of Z divided by Z of log Z with a minus sign. This is equal to FL. So this is the equation that determines what the Lagrange multipliers are going to be if you're given the expected values and vice versa. So this is a set of implicit equations. Typically, it's very difficult to solve. If I give you the expected value, can you find the Lagrange multipliers? It's determined by this. You're going to have to do it numerically. Computing the partition function can be a problem. But on the other hand, if you're given the partition function, and you want to figure out the expected value, that's trivial. Just take derivatives and you get it very easily. So what we have is we have solved the problem. In principle, we have to we maximize the entropy subject to the constraints, and what you get is distributions that are of the exponential type. Here I can detect the same mistake I made earlier. If I want to denote the sum with k, I better call this by a different letter. Very good. And so we have our expression for the probabilities, and we have our expression for how you compute the various Lagrange multipliers. One of them is the issue of computing the partition function, and the others are the problem of solving, once you have the partition function, solve for these implicit equations. And that's it. So what I would like to be able to do next time, in order to explore some more the consequences of this, is going to be, we're going to be doing things like, okay, the expectation value that we have here, for example, this could be the expected value of the energy. These are the energy of the microstates. The expected value of the energy is going to be the macroscopic variable. The appropriate probability distributions are going to be such that are going to be of this form, where you have a Lagrange multiplier and the energies, and the Lagrange multiplier corresponding to an energy is going to be what we call beta. So that's where temperatures are going to come in. And so what we're going to be doing over the next few classes is, in this completely general context, we're going to be exploring this mathematical formalism to extract as much juice as possible. See you next time.